In a previous lecture, I talked about electricity. This is kind of a follow-on lecture where I talk about circuits, which we talk about how to connect multiple components. We want to get into different ways of doing that. The concept are getting the three basic parameters of electric circuits: the current that flows, the voltage that drives the circuit, and the resistance that the components provide to the voltage. We want to show them the difference between series circuits and parallel circuits and introduce the relationship of the three parameters through Ohm's Law. So what I've shown them last time is they connect a battery holder, a bulb holder, and an open switch to form a circuit. They did this last time, so I won't actually have them go through it again. And I told them to close the switch and basically observe the bulb is going to light at a certain brightness. And I want them to kind of remember what that brightness looked like. Then I want to show them, well, three components, the bulb, the battery, and the switch, can only be really connected in one way to form a circuit. When we get into series circuits, we're talking about more components. And a series circuit is simply a circuit where there is only one path from the source through all the loads back to the source. So this is where we get the word circuit. It's a path, a single path through all the components. And there is a picture that we would draw that shows two loads. We could actually have as many loads as required down there in a row, as long as they continue to form one single path. So electricity now, the inner circle, the electricity is flowing from the battery, and it's going to each bulb, in this case, one at a time, back to the source. At this point, I introduce that current is a measure simply of how much electricity flows. And the unit is called amperes, or amps, and is designated with the symbol I. Now, any electrical component is going to resist the flow of current. And the way we measured that, we call it resistance. It's resisting the flow. And we use the letter R for that. And the unit that is measured is ohms. And that is represented by the Greek symbol omega, which we've shown here. The third parameter is going to be the voltage, which is the strength of the power source, and the unit of voltage is simply volt, or V. The fundamental relationship, which I've introduced before, but I want to emphasize in this lecture, is the relationship that voltage equals the current times the resistance, or if I divide both sides by resistance, I get that the current flowing is voltage divided by resistance. And I remind them that this is called Ohm's Law. Now, in building a circuit, series circuit, I point out that we connect a battery, two bulb holders, and an open switch in a series circuit. I have the battery, or the voltage source, two bulbs, and a switch. And we close the switch, and what we see, it's going to be a little hard for you to see in this video, is that the bulbs are on very dimly. It's unfortunate we're using only 1.5 volt battery, but compared to just one bulb, they're much dimmer. And that's what we're going to see. So now I'm going to ask the children to break into groups of probably 4 people each, 3 or 4 depending on how many are in the class. And I'm going to ask them to do this with an open switch, and then close the switch, and they for themselves can observe these bulbs. Now, we want to get an explanation for what happened, so we have here a little more, slightly more detailed diagram where we're going to call the loads, the resistances, R1 and R2. And we want to know how Ohm's Law can explain the change in the brightness. Well, the first thing they have to know is that when you put two loads in series, the resistances add. So now, remembering that the current is the voltage over the resistance, we want them to see that because we've increased the resistance, the current will be less. And if the current is less, the bulbs will not shine as brightly. Now we said, what happens if they add more bulbs, and we don't ask them to do it because they won't even be able to see them at that point. But the idea is that there'll be even less current flowing the bigger we make the resistance down here. Now, what would happen if one of these bulbs burned out? We want them to, the children, to spend a few moments speculating on what they think might happen. And then we can explain that the way a bulb works is there's a piece of wire called a filament that gets hot when electricity runs through it, and that's what causes light to come from it. But the mere fact that we're doing this means we're burning up the filament, and over time it simply disintegrates. And then we have the equivalent of a switch. It's like a broken wire. So when we have a broken wire, what would Ohm's law say about that? Well, the resistance just got very large. So essentially no current can flow, and therefore none of the lights will light. Now we asked them, this is a much better question to ask in December or January, when have you seen lots of light bulbs in a string? Because we want to refer them back to Christmas lights, either on a tree or on a building. And we asked them what would happen if one of these bulbs burned out, and that is no current would flow. Now, if you want to know what bulb to replace and you had 20 bulbs here, that could be a little bit difficult. We just talked about series circuits. The other kind of circuit we want to discuss is a parallel circuit. Now, a parallel circuit is a circuit that has not one path through all the components, but multiple paths from the source through all the loads and back to the source. If we cover up the load here, we would just have what we had before, other than the fact the load is shown here rather than down here, and we have a loop here, a path here, and another path going through load 1. So we have two separate paths. What happens is the electricity starts at the source. When the switch is closed, it comes to this point, but then it splits. Some of it goes there and some of it goes there. So electricity flows now to each bulb, not in turn, but simultaneously. So now I want the students to build a parallel circuit. I asked them to connect the holder and two bulbs and an open switch in this manner. Now this is a little more complicated for them because the way they will hook it up and what you see here are not necessarily identical. So they're going to have to figure out where on the circuit to make the different connections. In order to do this, they will probably need more wires than they used in the series circuit. So what we do is we give them a total of 6 wires. They shouldn't need 6, but we never know what configurations they might come up with, and we don't want them constrained by lack of wires. We want them to be able to figure out a way to do it, and maybe then they can figure a more efficient way. So then we ask them to close the switch and observe the bulbs. Now what should happen in this case, we ask them what happened. They should now see the bulbs being brighter again. A kind of peripheral question is whether a second switch could control only one of the bulbs. And we let them talk about, number 1, is the answer yes or no? And number 2, if the answer is yes, where would they put that switch? So what are some of the characteristics now? To simplify it, instead of having R1 and R2, I'm saying they're the same resistance, they're both R. Does Ohm's law explain the brightness? Well, if we look at the voltage, if we look at this load here, its resistance is R. And if we look at the source, its voltage is V. So we haven't changed anything from the original one bulb design. So that says we should see the same current flowing through this bulb and it should be just as bright. Now what happens if we add more bulbs in parallel? Well, the same argument. Each one has a resistance R and a voltage of V, so each one gets the same current. Now here's a question they won't be able to answer. Something has changed, because by magic, it seems, they've been able to light more bulbs with the same battery. The answer turns out to be that this source is being drained a lot faster. It will run out of power a lot faster because it's supporting more loads. Now, what would happen now if one of the bulbs burned out? Suppose load 1 burns out. Remember, that now becomes an open circuit. It's just another switch over here. Well, load 2 is still being powered by, we still see a loop here, and load 2 is being powered. So the answer that you're supposed to come up with is the remaining bulb or bulbs will be able to remain lit. So is this a better way to string 20 bulbs together? Well, yes, because when one burns out, we can see which one it is and immediately replace it. As a quick review, we want to highlight the main points of a series circuit and of a parallel circuit. Now, now that we know about series and parallel, we want to talk about what happens if you put batteries in series or parallel. And when two batteries are in series, the voltage adds. That's the important point to know here. So that in the picture on the left, there is twice as much voltage. Now, does that mean more or less current will flow in the circuit? So remember Ohm's law, what happens if we double the voltage? So the students should be able to answer that. When two batteries in parallel, the voltage stays the same. So one thing they should be aware of is if you're going to put them in parallel, you need the two batteries to be the same voltage. Don't try to put a 9-volt battery in parallel with a 1.5-volt battery, or you're going to cause some problems. Does this mean that more or less current flows to the bulb? And they should recognize if you haven't changed the voltage, there's not going to be more current. But if you're not going to get more current, why would you bother to do it? Well, it's the reverse argument of having one battery power multiple bulbs. In this case, what happens is the batteries will last longer. Now, I'm then going to go back to my lemon battery that I did at the end of the electricity lecture. The students found out that this lemon is simply not enough, doesn't generate enough voltage to light the bulb. So what I'm going to do is I'm going to come up with, I have 2 lemons and a light bulb. I will point out that the copper is the positive side of the battery, the zinc is the negative. So we'll connect the zinc on this battery to this lemon to the one side of the bulb, and we'll connect the copper on the other lemon to the other side of the bulb. And we ask them, will the bulb light? A lot of them will immediately say yes, forgetting the fact that there's not a circuit here. So then we connect the 2 batteries together. This may or may not light, depending on various circumstances. Before you connect them together, you can put a voltmeter across here and show the students that you've got somewhere around 1.5 or 2 volts, which should be enough to light a bulb. However, going back to what we previously discussed about the kind of battery and how much strength it really has, these batteries may simply be too weak, even though they have 1.5 volts. They just can't generate enough current. So you might find the result either way, depending on the quality of your lemons and how well you've hooked it together.